This tutorial will show how to use SAP 2000 to model staged construction of a cable-stayed bridge using the Construction Scheduler feature. It will have two spans, each 100 meters in length, with a single steel pylon 60 meters tall. The deck will be a concrete box section, 6 meters wide, and will be constructed in 10 stages. We start the process by clicking on File, New Model, and selecting the units as kilonewton meters. We will construct the model using only grids, so click on the Grid Only button. We will have a total of 3 grid lines in each direction. Click on the Define Coordinate Systems Grids command, and then the Modify Show button to bring up the Define Grid System data form. For the X direction, which is along the span, our coordinates will be -100, 0, and +100. In the Y direction, which is across the deck width, we will enter -3, 3, and 0. In the Z direction, which is vertical, we enter -10, 0, and 50. We will work in only one window, so close the Plan window and then go to the Define Section Properties Frame Sections command. Here we will add pipe sections to define a non-prismatic pylon. Make sure that the frame section property type is set to steel and click the Pipe button. We start with the bottom section and enter 1.2 meters for the diameter and 0.05 for the thickness. We will add another pipe section to model the pylon at the top. Here it has a diameter of 0.6 meters and then again a thickness of 0.05. Next, we take the previously defined sections and create a non-prismatic section. Select Other from the frame section property type and click the non-prismatic button. We will call it Pylon and use the top section as the start section and the bottom section as the end. It will be varied over the entire length in a cubic variation. Next, we zoom in on the pylon location and draw the pylon object. Starting at the top and going to the bottom to match our member definition. We leave the Draw mode and shut off the grids under the View menu. Next, we will draw joints to model the saddle locations for the cables. The first joint will be 4 meters below the top of the pylon. By clicking on the top of the pylon with the offset set to -4 meters, a joint is added. We leave the Draw menu, select the joint just drawn, and go to the Edit Replicate command. Here, we will add additional joints for the saddles at 2-meter intervals below the selected joint. This gives us a total of 9 cable to pylon connections. Next, we will modify the concrete material property to include time-dependent properties. Make sure that 4000 psi is selected, which is our concrete material, and click the Modify Show button. Check the Switch to Advanced Property display box, and then the Modify Show Material Properties button. Lastly, click the Time-Dependent Properties button. In this model, we will include both creep and shrinkage effects. We will set the shrinkage start age to be 3 days, and we'll use the full integration creep analysis type. Next, we will define the concrete box girder to be used for the deck. Select the material to be concrete and click on the Tube button. Input a depth of 1.2 meters, a width of 6 meters, a flange thickness of 0.2, and a web thickness of 0.3. Toggle the grids back on and switch to an XY plan view, and toggle down to the Z equals 0 level, which is the elevation of the deck. We will draw the deck as a single object from the pylon out to the right end. Click on the Select Mode button and select the frame object just drawn. Go to the Edit, Edit Lines, Divide Frames command and enter 10 to divide the deck into 10 segments. Next, we will define rigid links that span from the deck centerline to the deck edge where the cables connect. Click on the Fix All button to restrict any relative deformation. Before we draw the links, we will turn on the Snap to Lines option, and we'll window in for a better view. Click on the Draw to Joint Link command, and make sure that rigid link is showing in the property box. Click on the first joint to the right of the origin, select Vertical from the Drawing Control box, and click on the top grid line to draw one link. Right-click the mouse to stop drawing, and repeat the process for the rigid link on the other side of the deck. Zoom in even closer and select the two rigid links just drawn and go to the Edit Replicate command. and add links at 10 meters on center. Isolating our view on the right side of the bridge. Next, we will define the cable sections. Go to Define Cable Sections and add a new section. We will define the properties by using a diameter of 0.04 meters. Next, we will draw the cable objects. Make sure that the line object type and section are set to cable. Draw the cable from the lowest saddle point to the end of the first bridge segment. The cable geometry form automatically opens. Verify that the number of segments is set to 1, which is typically all we need due to the fact that catenary effects are automatically included in the cable, and make sure that the cable type is set to undeformed as we want the cables to be taut. Repeat the process for the next cable, going up one saddle point and out one bridge segment. Continue this drawing until cables have been added all the way out. Select all the cables using the Select Properties Cable Properties command. And go to the Edit Replicate command. We will use the Mirror tab and mirror the cables about the plane parallel to X to create cables on the other side of the deck. Now select the entire model and click on the pylon to unselect it. Again, click on the Edit Replicate command and then the Mirror tab. But this time, click on the mirror about plane parallel to Y. This will replicate the cables and deck on the left side span. To enhance the view, we will select the Extrude View option. And we will also turn off the grid lines and display the model in full 3D. Next, zoom into the base of the pylon so that we may assign support restraints. For the pylon, we will fix the base to restrict all translation and rotation. We will turn off the extruded view so that it will be easier to select objects. Next, we will select the right end of the bridge and assign a roller support. We will assign the same roller support to the left end as well. Next, we will assign objects to groups that will be needed to define the stage construction. Start by switching the view to a XZ plan and selecting the pylon. Go to the Assign to Group command and add a new group called Pylon. Next, select the deck segments just to the right and left sides of the pylon, along with the accompanying cables. There will be 4 cables in all, and assign them to a group called Deck 1. This will be the first deck construction stage. Repeat this procedure for the next group of decks and cables. And continue until all deck sections have been assigned to a group, finishing up with group Deck 10 that consists of just deck. The next step is to define the sequence of construction, which is where we will identify the tasks using the construction scheduler found under the Brim menu. Items input here will be converted into stages and cases under the load cases command. Stages may involve changes in the structure, application of load, and/or elapsed time during which creep, shrinkage, and material aging may occur. First, the model is saved. Next, click the Add New Schedule button and click OK for the default schedule name. We start by entering Superstructure as our first task description. This will be a summary task that will be used to group all the tasks associated with building the superstructure. The next task will be Pylon with a duration of 7 days. It has no predecessor task, and we click the Define Operations Toolbar button to display the operations form. Select Add Structure for the operation, select Pylon for the group, and use 0 days for the age it adds since the material is steel. In addition to the structure being added, check the Include Object Self-Weight checkbox and load this group with a load equal to twice the dead load. On the schedule, notice that the columns have been populated with the operation, object, and details including age, self-weight, and scale factor. Lastly, for this task, we will specify an output ID, also called Pylon. Select this task and click the Increase Indent Toolbar button to identify this task as a subtask of superstructure. Now we will add another task, this time for the first deck stage. Named Deck 1, it will have a duration of 3 days and will have a predecessor of Task 2, which means that it will not start until the completion of Task 2. This conditional relationship will be shown on the Gantt chart. Double-click on the Operations cell to bring up the operations form, and again we add structure, this time the group Deck 1, with an age at add of 14 days. Self-weight is checked with a dead load scale factor of 2. We specify Deck 1 for the output ID. Repeat this process until you have created tasks for all of the deck groups. Scrolling out, we can see how the tasks relate to one another on the Gantt chart. Next, we will add tasks after the construction to model the effects of time. We will input a task summary called post-build, and then a task called time 1 with a duration of 3 days, a predecessor of task 12, but no operations. This task is only meant to mark the passage of time. No structure is added or loaded. However, it is important to specify an output ID for if the task contains no operations and the end stage and end case checkboxes are not marked, the program will ignore the task unless the output ID is specified. Continue to add time tasks, with the last task having a duration of 3,000 days. Older concrete is less sensitive to time and thus may have a longer duration step. It is important to realize that task duration can have a significant impact on creep calculations. Select the post-build task and click on the Decrease Indent button to identify this task as a summary task. Again, we can see the relationship between tasks, including summary tasks and subtasks. Before we leave the construction scheduler, select P-delta from the Geometric Nonlinearity Parameters drop-down list to include P-delta effects in the pylon and deck, and click the Modify Show button for nonlinear parameters. Make sure that the Time-Dependent Material Properties option is checked, so that creep and shrinkage effects are included for the concrete material. We are now ready to leave the construction scheduler. As we exit, the scheduler generates the stages and load cases for the nonlinear static analysis. Click the Define Load Cases command, and we see that a Sched 1.0 load case has been created from the construction scheduler input. This load case is locked, meaning that no changes may be made to it using the Modify Load Case button. Changes can only be made in the scheduler. On occasion, however, we may want to make some changes directly to the load case, in which case we first need to make a copy and then edit the copy. Name our copy case Bridge, and note that the stage construction load cases are a type of nonlinear static analysis. Also note that the P-delta has been selected as done on the scheduler. The construction scheduler typically creates 2 stages for each task, a duration stage with no operations and a 0 duration task at the finish day where operations are carried out. Click on the Modify Show button for results saved, and make sure that there are adequate number of steps assigned for the time-dependent items. We will use 5 for this model. Now we are ready to run the analysis. For this model, we will not run the dead, modal, or Sched 1 cases. Only the copied bridge case for the static nonlinear stage construction analysis. The analysis window shows how the program steps through each stage. Once the analysis is complete, we will display the moment diagram in the deck for a particular step. For the step we selected, step 60, the bridge is only partially complete. We can create a video showing the sequence of bridge construction along with the varying moments in the deck, including both construction and time effects. Next, display the undeformed shape. Next, we will display the longitudinal deflection of the deck mid-span versus time. The point selected is joint 46. And we will limit the horizontal time axis to 300 days. Next, we will plot the axial force in 3 cables as it varies with time. This time, we will limit the time axis to 45 days. It is easy to see the 3 distinct starting times for the 3 cables. Lastly, we will plot the moment mid-span as it varies with time. This concludes this tutorial.